Schrödinger's cat is a thought experiment, sometimes described as a paradox, devised by Austrian physicist Erwin Schrödinger in 1935. It illustrates what he saw as the problem of the Copenhagen interpretation of quantum mechanics applied to everyday objects. The scenario presents a cat that may be simultaneously both alive and dead, a state known as a quantum superposition, as a result of being linked to a random subatomic event that may or may not occur. The thought experiment is also often featured in theoretical discussions of the interpretations of quantum mechanics. Schrödinger coined the term Verschränkung, entanglement, in the course of developing the thought experiment. Origin and motivation. Schrödinger intended his thought experiment as a discussion of the EPR article named after its authors Einstein, Podolsky, and Rosen in 1935. The EPR article highlighted the bizarre nature of quantum superpositions, in which a quantum system such as an atom or photon can exist as a combination of multiple states corresponding to different possible outcomes. The prevailing theory, called the Copenhagen Interpretation, said that a quantum system remained in this superposition until it interacted with, or was observed by, the external world, at which time the superposition collapses into one or another of the possible definite states. The EPR experiment showed that a system with multiple particles separated by large distances could be in such a superposition. Schrödinger and Einstein exchanged letters about Einstein's EPR article, in the course of which Einstein pointed out that the state of an unstable keg of gunpowder will, after a while, contain a superposition of both exploded and unexploded states. To further illustrate, Schrödinger described how one could, in principle, create a superposition in a large-scale system by making it dependent on a quantum particle that was in a superposition. He proposed a scenario with a cat in a locked steel chamber, wherein the cat's life or death depended on the state of a radioactive atom, whether it had decayed and emitted radiation or not. According to Schrödinger, the Copenhagen interpretation implies that the cat remains both alive and dead until the state has been observed. Schrödinger did not wish to promote the idea of dead and alive cats as a serious possibility. On the contrary, he intended the example to illustrate the absurdity of the existing view of quantum mechanics. However, since Schrödinger's time, other interpretations of the mathematics of quantum mechanics have been advanced by physicists, some of which regard the alive and dead cat superposition as quite real. Intended as a critique of the Copenhagen interpretation, the prevailing orthodoxy in 1935, the Schrödinger's cat thought experiment remains a defining touchstone for modern interpretations of quantum mechanics. Physicists often use the way each interpretation deals with Schrödinger's cat as a way of illustrating and comparing the particular features, strengths, and weaknesses of each interpretation. Thought experiment. Schrödinger wrote, "One can even set up quite ridiculous cases. A cat is penned up in a steel chamber, along with the following device, which must be secured against direct interference by the cat in a Geiger counter. There is a tiny bit of radioactive substance, so small, that perhaps in the course of the hour one of the atoms decays, but also, with equal probability, perhaps none. If it happens, the counter tube discharges and through a relay releases a hammer that shatters a small flask of hydrocyanic acid. If one has left this entire system to itself for an hour, one would say that the cat still lives if meanwhile no atom has decayed. The first atomic decay would have poisoned it. The psi function of the entire system would express this by having in it the living and dead cat, pardon the expression, mixed or smeared out in equal parts. It is typical of these cases that an indeterminacy originally restricted to the atomic domain becomes transformed into macroscopic indeterminacy, which can then be resolved by direct observation. That prevents us from so naively accepting as valid a blurred model for representing reality. In itself, it would not embody anything unclear or contradictory. There is a difference between a shaky or out-of-focus photograph and a snapshot of clouds and fog banks. Schrödinger's famous thought experiment poses the question, when does a quantum system stop existing as a superposition of states and become one or the other? More technically, when does the actual quantum state stop being a linear combination of states, each of which resembles different classical states, and instead begin to have a unique classical description? If the cat survives, it remembers only being alive. But explanations of the EPR experiments that are consistent with standard microscopic quantum mechanics require that macroscopic objects, such as cats and notebooks, do not always have unique classical descriptions. The thought experiment illustrates this apparent paradox. Our intuition says that no observer can be in a mixture of states, yet the cat, it seems from the thought experiment, can be such a mixture. Is the cat required to be an observer, or does its existence in a single well-defined classical state require another external observer? Each alternative seemed absurd to Einstein, who was impressed by the ability of the thought experiment to highlight these issues. In a letter to Schrödinger dated 1950, he wrote, "You are the only contemporary physicist, besides Law, who sees that one cannot get around the assumption of reality, if only one is honest. Most of them simply do not see what sort of risky game they are playing with reality as something independent of what is experimentally established. Their interpretation is, however, refuted most elegantly by your system of radioactive atom and amplifier and charge of gunpowder and cat in a box, in which the psi function of the system contains both the cat alive and blown to bits. Nobody really doubts that the presence or absence of the cat is something independent of the act of observation. Note that the charge of gunpowder is not mentioned in Schrödinger's setup, which uses a Geiger counter as an amplifier and hydrocyanic poison instead of gunpowder. The gunpowder had been mentioned in Einstein's original suggestion to Schrödinger 15 years before, and Einstein carried it forward to the present discussion. Interpretations of the experiment. Since Schrödinger's time, other interpretations of quantum mechanics have been proposed that give different answers to the questions posed by Schrödinger's cat of how long superpositions last and when, or whether, they collapse. Copenhagen Interpretation. A commonly held interpretation of quantum mechanics is the Copenhagen Interpretation. In the Copenhagen Interpretation, a system stops being a superposition of states and becomes either one or the other when an observation takes place. This thought experiment makes apparent the fact that the nature of measurement, or observation, is not well defined in this interpretation. The experiment can be interpreted to mean that while the box is closed, the system simultaneously exists in a superposition of the states decayed nucleus/dead cat and undecayed nucleus/living cat, and that only when the box is opened and an observation performed does the wave function collapse into one of the two states. However, one of the main scientists associated with the Copenhagen interpretation, Niels Bohr, never had in mind the observer-induced collapse of the wave function, so that Schrödinger's cat did not pose any riddle to him. The cat would be either dead or alive long before the box is opened by a conscious observer. Analysis of an actual experiment found that measurement alone, for example by a Geiger counter, is sufficient to collapse a quantum wave function before there is any conscious observation of the measurement, although the validity of their design is disputed. The view that the observation is taken when a particle from the nucleus hits the detector can be developed into objective collapse theories. The thought experiment requires an unconscious observation by the detector in order for waveform collapse to occur. In contrast, the many worlds approach denies that collapse ever occurs. Many worlds interpretation and consistent histories. In 1957, Hugh Everett formulated the many worlds interpretation of quantum mechanics, which does not single out observation as a special process. In the many worlds interpretation, both alive and dead states of the cat persist after the box is opened, but are decoherent from each other. In other words, when the box is opened, the observer and the possibly dead cat split into an observer looking at a box with a dead cat, and an observer looking at a box with a live cat. But since the dead and alive states are decoherent, there is no effective communication or interaction between them. When opening the box, the observer becomes entangled with the cat, so observer states corresponding to the cats being alive and dead are formed. Each observer state is entangled or linked with the cat so that the observation of the cat's state and the cat's state correspond with each other. Quantum decoherence ensures that the different outcomes have no interaction with each other. The same mechanism of quantum decoherence is also important for the interpretation in terms of consistent histories. Only the dead cat or the alive cat can be a part of a consistent history in this interpretation. Roger Penrose criticizes this. I wish to make it clear that, as it stands, this is far from a resolution of the cat paradox. For there is nothing in the formalism of quantum mechanics that demands that a state of consciousness cannot involve the simultaneous perception of a live and a dead cat. However, the mainstream view, without necessarily endorsing many worlds, is that decoherence is the mechanism that forbids such simultaneous perception. A variant of the Schrödinger's cat experiment, known as the quantum suicide machine, has been proposed by cosmologist Max Tegmark. It examines the Schrödinger's cat experiment from the point of view of the cat, and argues that by using this approach, one may be able to distinguish between the Copenhagen interpretation and many worlds. Ensemble interpretation. The ensemble interpretation states that superpositions are nothing but subensembles of a larger statistical ensemble. The state vector would not apply to individual cat experiments, but only to the statistics of many similarly prepared cat experiments. Proponents of this interpretation state that this makes the Schrödinger's cat paradox a trivial matter, or a non-issue. This interpretation serves to discard the idea that a single physical system in quantum mechanics has a mathematical description that corresponds to it in any way. Relational interpretation. The relational interpretation makes no fundamental distinction between the human experimenter, the cat, or the apparatus, or between animate and inanimate systems. All are quantum systems governed by the same rules of wave function evolution, and all may be considered observers. But the relational interpretation allows that different observers can give different accounts of the same series of events, depending on the information they have about the system. The cat can be considered an observer of the apparatus, meanwhile, the experimenter can be considered another observer of the system in the box, the cat plus the apparatus. Before the box is opened, the cat, by nature of its being alive or dead, has information about the state of the apparatus. The atom has either decayed or not decayed, but the experimenter does not have information about the state of the box contents. In this way, the two observers simultaneously have different accounts of the situation. To the cat, the wave function of the apparatus has appeared to collapse. To the experimenter, the contents of the box appear to be in superposition. Not until the box is opened, and both observers have the same information about what happened, do both system states appear to collapse into the same definite result, a cat that is either alive or dead. Transactional interpretation. In the transactional interpretation, the apparatus emits an advanced wave backward in time, which combined with the wave that the source emits forward in time, forms a standing wave. The waves are seen as physically real, and the apparatus is considered an observer. In the transactional interpretation, the collapse of the wave function is atemporal and occurs along the whole transaction between the source and the apparatus. The cat is never in superposition. Rather, the cat is only in one state at any particular time, regardless of when the human experimenter looks in the box. The transactional interpretation resolves this quantum paradox. Zeno Effects. The Zeno effect is known to cause delays to any changes from the initial state. On the other hand, the anti-Zeno effect accelerates the changes. For example, if you peek a look into the cat box frequently, you may either cause delays to the fateful choice or, conversely, accelerate it. Both the Zeno effect and the anti-Zeno effect are real and known to happen to real atoms. The quantum system being measured must be strongly coupled to the surrounding environment, in this case to the apparatus, the experiment room, etc., in order to obtain more accurate information. But while there are no information passed to the outside world, it is considered to be a quasi-measurement, but as soon as the information about the cat's well-being is passed on to the outside world, by peeking into the box, quasi-measurement turns into measurement. Quasi-measurements, like measurements, cause the Zeno effects. Zeno effects teach us that even without peeking into the box, the death of the cat would have been delayed or accelerated anyway due to its environment. Objective collapse theories. According to objective collapse theories, superpositions are destroyed spontaneously, irrespective of external observation, when some objective physical threshold, of time, mass, temperature, irreversibility, etc., is reached. Thus, the cat would be expected to have settled into a definite state long before the box is opened. This could loosely be phrased as the cat observes itself, or the environment observes the cat. Objective collapse theories require a modification of standard quantum mechanics to allow superpositions to be destroyed by the process of time evolution. Applications and tests. The experiment as described is a purely theoretical one, and the machine proposed is not known to have been constructed. However, successful experiments involving similar principles, e.g. superpositions of relatively large, by the standards of quantum physics, objects have been performed. These experiments do not show that a cat-sized object can be superposed, but the known upper limit on cat states has been pushed upwards by them. In many cases the state is short-lived, even when cooled to near absolute zero. A cat state has been achieved with photons. A beryllium ion has been trapped in a superposed state. An experiment involving a superconducting quantum interference device, SQUID, has been linked to the theme of the thought experiment. The superposition state does not correspond to a billion electrons flowing one way and a billion others flowing the other way. Superconducting electrons move en masse. All the superconducting electrons in the SQUID flow both ways around the loop at once when they are in the Schrödinger's cat state. A piezoelectric tuning fork has been constructed, which can be placed into a superposition of vibrating and non-vibrating states. The resonator comprises about 10 trillion atoms. An experiment involving a flu virus has been proposed. An experiment involving a bacterium and an electromechanical oscillator has been proposed. In quantum computing, the phrase cat state often refers to the special entanglement of qubits wherein the qubits are in an equal superposition of all being 0 and all being 1, e.g. psi equals 1 2, 0 0, 0 plus 11, 1. Display style psi wrangle equals frac 1 sqrt2 big 0 0 l dots 0 wrangle plus 11 l dots 1 wrangle big dot psi wrangle equals frac 1 sqrt2 big 0 0 dots 0 wrangle plus 11 dots 1 wrangle big. Extensions. Wigner's friend is a variant on the experiment with two human observers. The first makes an observation on whether a flash of light is seen and then communicates his observation to a second observer. The issue here is, does the wave function collapse when the first observer looks at the experiment, or only when the second observer is informed of the first observer's observations? In another extension, prominent physicists have gone so far as to suggest that astronomers observing dark energy in the universe in 1998 may have reduced its life expectancy through a pseudo-Schrödinger's cat scenario, although this is a controversial viewpoint.
Please subscribe and thanks for watching.